Very welcome, kids. Today, I'm going to continue on the discussion about the PWM. We are going to practice a little bit more problems on how to calculate the right resistance, the right capacitance for the filter circuit. I'm going to continue from where I left last session. And of course, at some point, if the time is still allowing, I'm going to activate your quiz, and then you are going to have a quiz. The quiz is going to be about the analog to digital, not PWM. About the PWM, I'm going to quiz you next week. So stay with me. Today, most of the session, I'm going to practice solving problems, right? Instead of too much of theory. And of course, at some point, I'm going to show you what's the application of what you are going to learn today, which is really helpful. Once again, for your capstone project, I'm pretty sure most of you are going to use a DC motor, probably even a stepper motor at some point in order to finish up a little bit of your capstone project. Maybe it's a good time to learn about PWM control. If I'm going to summarize what I've talked about it last week, I mean, not last week, it was Monday, last session. It was all about pulse width modulation. Remember, I said whatever we've discussed earlier, it was about having analog inputs into the system, and then we were trying to convert it to digital output. But in there, I was introducing the method called analog to digital converter. Still, we are trying to convert the type of signal from analog to digital, but this time I'm practicing with you how to use PWM method, right? And look at pulsing, converts the input signal to some pulse, such as 0 and 1, and through this pulse width, you can convert analog to digital. More detail, if I want to open it up, during the interrupt timer and during the analog to digital conversion discussion, my focus was mostly on having input into the system. I was trying to teach you how we can have some signal as an analog to become the input of our system. But in pulse width modulation, the focus is not on input anymore. Focus is going to be on output. Therefore, still we are trying to convert, still we are trying to change the signal format, but the focus in pulse width modulation is how to control the output. In there, we were more focused on how to control or how to define the right input to the system. Thus, a little bit of difference between analog to digital conversion and pulse width modulation. Having this in mind, I'm going to go back to the example. Remember, I finished it right in here last session. The recording of last session is already posted on YouTube. You are more than welcome to go watch it, update yourself in case you need more detail in there. Definitely either drop your question under the video or just on the discussion frame on Avenue. Either will work. I'll try my best to get back to you as soon as possible. So remember, I was trying to just calculate. Still, I do have it on the other side, right in here inside the OneNote. This is what we did. Example 2, I already calculated the first order low pass filter. I was trying to show you how to find out the right capacitance, the right resistance. In a circuits that we have a capacitor right in here, I have a capacitor. I do have R1 as a resistance. And then I do have our load, right? So I'm having 3 components included in the system. Such a simple system is called, what I said earlier, is called a low pass filter. Low pass filter. This is a low pass filter. And we are trying to figure out how we can eliminate noise in the system in order to have a more accurate output. This is the actual target for this one. So now in example 2, example 1, I already calculated the cutoff frequency. Remember, this is the cutoff frequency. Now I'm going to continue with another example. In this example, definitely you have the option also to, if you follow me, to remind yourself what was the basic of pulse width modulation. Earlier, I introduced online calculator. It's available right in here. I'm gonna also practice how to use it one more time. And you guys also later, in case you are in any environment other than learning environment, instead of going through the calculation yourself manually, definitely you can use the online calculator in order to figure out the right capacitance and the right resistance for your filter system. So let's continue with example 2. Before that, anyone who has any question for me, feel free to ask. Anything that we discussed earlier, if you have a question about it, I'm fully available to answer your question. So let me remind you what we had in here. In here, I calculated my load resistance. In order to just consider the load resistance in here, I said that my filter, the one that I designed using the capacitance and the resistance, my filter resistance is selected much smaller than the load resistance, right? This is my filter resistance, right? It's going to be really smaller than what I have for the filter resistance. So load resistance will not change the cutoff frequency if it is smaller. That's the reason. I need to still keep the cutoff frequency constant or like the same value. So I needed to calculate the gain, and I told you how we calculate the gain one more time before I start the next example in order to remind you a little bit of mathematical expression. I'm pretty sure you guys already know it, but I go through it one more time. We all may forget. So I'm calculating gain, kids, in here. What I did, it was gain, and the unit is decibel. So in order to calculate gain, this is the required equation. This is not inside the lecture slide. I'm going to just explain it just as a reminder in case anyone forgot about them. So this is going to be 20 log 10, any output voltage. You may want to take a note in case you need it. Otherwise, just listen to what I'm explaining. And then this is going to be your input voltage. So initially, when the output voltage is given, usually output and input, they might be equal. If these two are equal, then gain in decibel, gain is 20. If I'm going to say V out, call this one V out, call this one V in. If V out and V in are equal, then I'm going to have 20 log 10. Then this becomes 1, right? If they are equal. Then if log 10, 1 is 0, then I'm going to have gain to be 0. But how about the gain at cutoff frequency? If I'm going to look at gain at cutoff frequency, then I'm going to have V out or output voltage over V in 1 over root 2 of 2, right? So then gain is going to be from here. I'm going to write it down in here. In dB is going to be 20 log 10. If you calculate this one, it's going to be 707. And then it becomes something like minus 3 dB. Right? So this is a quick summary of how we calculate. Now, having that in mind, I'm going to look at how we calculate the ripple voltage. Since we are trying to filter a signal, and that signal is going to be a digital value at the end of the day, and everybody knows digital value means either 1 or 0, then what we need to convert it into a continuous value, which we are going to have a signal, something like, probably if I'm going to draw it in a different color right in here, we are going to have something like this, right? So this is fluctuating and become like a ripple. That's why we call it ripple voltage, right? We need to calculate it using this equation. How do we calculate V ripple? I'm going to call it VR. We have to say 3V PWM. Either we have it based on the problem that we are solving, or we have to calculate it times 10 to the power of, the review in here about the log, now you need it right in here. Log frequency of PWM, that's why I reviewed the log with you, over the frequency of the capacitor. So this is how you calculate your ripple voltage. Frequency of the cutoff voltage, usually we have to change the frequency of the PWM or the frequency of the cutoff voltage to have a more accurate ripple voltage, right? Either the frequency of the PWM or the cutoff voltage. Make sense? Now, we wanted to practice this one using an example. I'm gonna just leave it in there. If you need it, you can later watch the recording again. So example is asking me, determine the ripple voltage of filter in example 1. If it is filtering 10 volts PWM, how do I calculate this one? Part 1 in this example is asking me, let's say P1. This is example 2 of the PWM section. I've already posted the solution for you later. If you would like to, you can go back or just watch the recording again. So I'm going to calculate the ripple voltage of filter in example 1. If it is filtering at 10 volts PWM, so it means my V PWM is 10 volts. And what's the frequency? With the frequency of 10 kilohertz, frequency of PWM is going to be 10 kilohertz. And I'm going to consider 50% duty cycle. Duty cycle is 50%. These are the information I'm just using from the problem. Now, part 2 is asking me, design your filter circuit to make 0.5 volts ripple voltage of step 1. So one by one, let's go over part 1 first. Therefore, I'm going to calculate it using the same equation I just explained, which is V ripple. Even it is right in here. I'm using this equation. R stand for ripple. Then I'm going to say 3V PWM, I already have it, times 10 to the power of minus log frequency of PWM over frequency of cutoff frequency. This is the cutoff frequency of the filter. Remember, this is cutoff frequency of the filter, just for your reference. I put it down right in here. Now, I just need to take the numbers from the problem and I substitute them. For example, in here, 50% of duty cycle is going to be VPWM. I just rearrange it, okay? 0.5 times 10 volts means 5 volts for the PWM voltage, right? Now, if I have that one, I can say V ripple is 3 times 5 volts times 10 to the power of minus log. I have 10 kilohertz for the PWM frequency, and I have 1 kilo for the cutoff frequency of the filter. Using those, I'm going to have 1.5 volts. What is this 1.5 volts? In fact, this is going to be the 10 volts with duty cycle of 50%. So my power source is going to be the 10 volts with the duty cycle of 50%. So then the steady voltage will be 5 volts. And from there, then I'm having the ripple voltage frequency of 10 kilohertz to be 1.5. Make sense? Now, if we go back right in here, if we just put all of those numbers in here, like for example, remember the resistance was 1.5 resistance from the circuit. it was given C was 1, and all I need in here, this one is 10, and duty cycle, remember duty cycle is supposed to be 50%. If I put it down right in there, and if I hit the calculator, it should find out the same thing. This is somehow validating. This is somehow, I received another update for the B103. Still, they are working. If anything new, any new information, they said they are going to update me, and I'll update you if it is coming before the end of the class. So then I'm going to have the same in here. So it has to be, in order to validate, it has to be peak-to-peak voltage. I found it has to be 1.5. In here also, it should be exactly the same 1.5. This is my cutoff. This is my peak-to-peak voltage for, what did I use the, oh, okay, this one should be 10. I had it 10. Calculate. It's going to be 1.5. You can see it right in here. So it is validating my calculation. Now, if you look at what is that 1.5 based on this picture, simply means because this is going to be peak to peak. Peak to peak means just from this point to this point. This is what we call it, from here to here. It's going to be 1.5 volts. Any questions so far? No? Then we can go back and calculate part 2. Part 2 is asking now, go ahead, design a filter to make 0.5 volt ripple voltage of a step 1. How do we do that? So I'm going to say now, I'm going to have my V ripple to be 0.5 volt. Still, I'm having duty cycle to be 50% of the VH or the high. Still, it's going to be the same, 10, right? 10 volts. Those are still the same. Now, what is my new calculation? VR is 3V PWM 10 to the power of log, again, still frequency of PWM over cutoff frequency. And then now you have like 0.5 from here, 0.5. Then the rest is going to be whatever number we had in here. I'm going to just substitute. It's going to be 3 times 50% of the duty cycle times, what was the VH? 10 volts. And if you calculate this one, still you have to add this part. I'm going to make a little bit more space in here. So now you can see the whole calculation. So then right after that, you have like 10 minus log. What was the frequency? Frequency was 10 kilohertz over frequency of the cutoff voltage. Now we have to figure it out. We don't have the new cutoff frequency. Therefore, this is going to be our question to solve. Then from there, if I substitute, it becomes log 0.5. I rearrange it 3 times 5. It becomes minus log 10 from here, 10 kilohertz over cutoff frequency. Then from here, what you have is going to be 0.5 over 15 cutoff frequency over 10K. And then from here, you simply can calculate what is the cutoff frequency. So your cutoff frequency is 0.33 kilohertz. Now, having cutoff frequency of 330 hertz or 0.33 kilohertz, that will help me now to calculate so now I have the cutoff frequency is 1 over the frequency of the capacitor is 2 pi. Remember, we had it last session. I had this one for you last session. 2 pi R1, C1. This is from last session. It's in the previous slide. If this one is 30.33 kilohertz, or let's say 330 hertz, then how I can figure out my R1, C1 to design my filter system? Then I have to say my R1, C1 is going to be 0.47. If I want to really be accurate, this much, very close to 0.5. This is my R1, C1. Now, we can use log on both sides of the equation. Therefore, I'm going to say log 0.5. If I already did that part for you, I just explained. I can just use the log. So I'm going to now use it in order to calculate the C1 and R1. Therefore, any combination of the resistance and capacitance is going to be this one. If the combination of like the capacitance and the resistance is this one, the smallest resistance will be the best. So I have to say the best choice is the best is the smallest resistance. This is the best choice. Yeah.
Where did that 15 come from? 0.5.
3 times 5.
Oh, where did the 5 come from? Was it at 3 and then 50%? So shouldn't that be 1 point?
No, I calculated that one before. I calculated. This one is coming from here.
Oh, no, I found it.
Yeah?
Yeah.
Okay. It's coming from them. So now, we have also to look at available capacitance. So the smallest resistance is like the best option. For the capacitance also, then I'm going to just come up with some idea. For example, in case I select capacitance C1 to be 0.1 microfarad, then what would be my resistance R? Then I'm going to have my R1 to be 4.77 kilo ohm. Based on the available capacitors, you can select proper resistors for real application. Therefore, again, you can go back, use the online calculator, which I already show you right in here. You can just adjust the information. Right now, you have a new capacitance, a new resistance. Definitely, you can, again, calculate the cutoff frequency. You can calculate the peak-to-peak frequency. All of them are something you can, all you need to change in here. Before it was 15900, just change it to the new one. Suppose that you have it like 477. This is in ohm. That's why I converted. What I calculated is kilo ohm. In ohm, it becomes 4770, right? And about capacitance, remember I said if I'm going to change it to 0.1, all you need is change here to 0.1. And then the remaining, such as, for example, your cutoff frequency is supposed to stay as it is. Your VH supposed to stay as it is. You don't change any of those, and then hit the calculator. Right after that, still you can see, so you have in here, let it calculate. So you have your 10K, you have your 50, 10, 1K point. Okay, this is microfarad. Then add U in here to calculate properly. Then you can see you have the cutoff frequency, the ripple voltage. You have again your cutoff frequency, and then you have to also, instead of cutoff frequency, choose the RNC. If you want the RNC, then you are giving this new one. Again, you calculate, then the peak to peak will change. Peak to peak will become exactly what you have been asked, which was like 0.5. Look at here, this is now 0.5. Again, peak to peak means from this point to this point. I was asked to keep it to 0.5. The calculation in there, it is validating whatever we have in here. Now, knowing all of this, I'm going to look at a picture of any question before I move to the next one. Everyone got the point? So I'm going to look at the op amp again. Op amp is something I already discussed it last week, but one more time. Usually op amp has like 5 pins. 2 input is always there, 1 output is always there, and 2 other input, the one on here, and of course on here is coming from the source. Okay, so who can remind us what is the application of the op amp? Why we use it in electrical circuit? What's the purpose? Who can remind us? We had it last week. Any idea? Op amp, as the name is just somehow showing, supposed to amplify, right? It's supposed to amplify the differential between the 2 input. Remember I said I'm having 2 input, inverting and non-inverting, right? Inverting and non-inverting means right in here. So I'm having 2 input in here. Op amp is amplifying the differential between these 2 inputs and the output result. So now, if I'm using PWM, simply means still I'm having 2 inputs. In here, you can see one of my input is a sawtooth wave. What is a sawtooth wave? In case you are not familiar, any wave like this is considered a triangular wave, okay? If this is my triangular wave, in this situation, if I draw a line right in here, simply means I'm having a T1 and T2. What is T1 and T2? T1 is my rise time. T2 is my fall time. In case I'm having T1 and T2 to be equal, means rise time and fall time, both of them are equal, then the wave is called a triangular wave. It could be the input for pulse width modulation through an amplifier. But in situation that T1 is not equal to T2, simply means this wave is going to change to something like this. In that situation, maybe better to draw it in OneDrive. I have more space in here. In that situation, my rise time and my fall time are not equal anymore. And that's why I call it a sawtooth waveform. It's like this one. So it's going to be like this. Now, if I draw a line right in here, suppose this is my rise time, and I'm having T1, and this is T2, which is going to be my fall time, and this is my rise time, right? Then these two are not equal. This, let's say T1 and T2 are not equal. So this is a sawtooth. Usually for pulse width modulation, I'm having both examples in here. So here I'm having a sawtooth, another signal in here. Both of them, one of them is my inverter input, the other one is non-inverter input to the amplifier. And still my output right in here is supposed to be a PWM output, right? But I have another example in here. I'm going to maximize again. This example, you can see I'm having, again, one signal coming to here. And this signal, if I draw the line for you, is coming from this linear signal, right? So then, and I'm having a triangular signal from this triangular wave going to my non-inverting input. And then output supposed to be PWM. PWM supposed to be a digital waveform. A digital waveform means either 1 or 0. Therefore, I draw this output right in here. Follow me, I'm tracing the line. Simply means this is my PWM output right in here. A combination of 0 and 1. Pulses of 1 and 0. Of course, these periods are this T1 and T2, based on which kind of wave is going to be my input. If it is a sawtooth waveform, therefore on and off are not equal. I mean the time for time of rise, time of fall are not equal. If it is triangular like this green waveform right in here, you can see your on and off. Suppose this is 5 seconds. This one is also 5 seconds. Both of them are equal. Any questions so far? Now, having this in mind, you simply can understand what's the application of this amplifier. Also, I show amplifier. This is the symbol for amplifier in electrical circuit, but the actual component is in real world, in real application, is this black IC right in here. All those circuit, all those like components are inside this one. This is your actual amplifier. So in fact, I would say that comparator amplifier, the name is somehow talking, means you are having some signal. In here, you've got a sawtooth signal and a signal. Supposed to compare this two with the output. That's why we call it a comparator. In here, I mentioned it. We call it a comparator amplifier. And it is comparing these two signals in order to generate a PWM signal as an output. Make sense? Why we use amplifier now? So having that in mind, let's just look at quickly one application of why we learn this stuff, especially for DC motor. It's a short video. I'm gonna just show it to you right in here. This is one application. Look at here, what do I have in here? I have the PWM, exactly same circuit I show you inside this slide. I'm having PWM output, and the input, it was a triangular waveform. I'm trying to look at this DC motor. I'm trying to control the DC motor through the amplifier, even without the microcontroller. This is exactly the same DC motor you have in the lab. That's why I say this is really something functional, and you can use it for your capstone project, even if you do not want to use microcontroller and programming. So you can see if you have a path, right now this DC motor can simply be controlled and go through a circle or any other map that you are uploading in there. Shortly, you will see that it is moving through a certain path. Like a little robot, a simple little robot. Which kind of sensor it might come to your mind that we can add to this one and make it an advanced project? More specifically for automotive application. So isn't that cool? So I just show you this one as an application. Of course, I made it available to you. You can just, if you want, rewatch it later on Avenue. So I'm going to just go over one more example for you. If the time allows, still we have a few more minutes. One more example, and then I'm going to give you the quiz. So I leave this for your reference. Later, you can come back to this one. So another example, this part of the lecture is going to be the lab portion. I'll cover it for you during the lab time. I'm going to introduce the PWM register, very similar to what we did for interrupt timer, what we did for analog to digital register. Again, you need to use, we do have a register. And inside the lab, we are going to practice how to use the PWM register, how to just program our microcontroller through the 8-bit counter, adjust the duty cycle register. Duty cycle register, why we need duty cycle? Remember, kids, I said duty cycle is helping to control the speed, right? Duty cycle means the speed control. Therefore, we do have a register to just go ahead, which is PWM DTYN, stand for duty cycle. We can control the speed through that one. So the very next one, these are all what I'm going to teach you during the lab time. I'm going to cover example 3 for you, and then I'll activate your quiz. Example 3, who can remember what is XTAL? We had it before. One more time. XTAL stand for your bus frequency or crystal frequency. Remember, we had it last week as well. So now I'm having this question. Assume your crystal frequency or X. This is example 3. Example 3 is asking your crystal frequency is given to be 4 megahertz. 4 mega, if you want the bus frequency, means divided by 2 to calculate your bus frequency. Therefore, bus frequency is 2, means crystal frequency divided by 2. Bus frequency means crystal frequency divided by 2. Remember, we had it like this. This is the crystal frequency, XTAL. And then if we have this one, I'm going to draw it for you. Divided by 2, then you can find out the bus frequency. And then if you do have a PWM register right in here, this is your PWM, PRCLK. This means you are going to divide it by 2 to the power of n, and n could be 0 to 7. Because we have it 8-bit, right? Therefore, if you want to calculate the clock A, you have to consider the information for the PWM SCLA. Again, means divided by 2n this time, right? Again, but this time n starts from 1 to 256, right? And then output in here is going to be your clock SA, right? So now, what's the purpose in here? I'm going to, these clock SA kids, these are the PWM clock frequency. So I'm gonna call them frequency of PWM. These are the clock frequency. So now, solution, for example, I'm going to say highest frequency, FH. I'm going to call FH highest frequency of clock A is going to be my main bus frequency. Main bus frequency in here is 2. So this is going to be the, I call it FM, means the main bus frequency, times my prescaler, times my scalar. Prescaler and a scalar. My prescalar start, this is my prescaler. It's gonna start from 0. A scalar start from 1. Look at here. A scalar is starting from 1. This is my scalar. This is my prescalar. From those, I don't guess them. Now, I substitute the number. Then I'm having 2 megahertz over 2 to the power of 7 times, what was it? 500, because maximum in here is 250. If I have 2 times 250, then 2 times 250 simply becomes, then I'm going to consider 512. This is 6, 256. 2 times 256 is coming from here, from the scalar. Don't confuse where those numbers are coming from the register for PWM from the data sheet, kids. I'm taking those from the data sheet. If it is an exam, I'll give them to you, or I give that part of the data sheet as a reference for you to read them and find the right information. So then simply I have like my highest frequency to become 30, right? My highest frequency in here is actually 30. Any question for me? So one more time, I'm gonna double check for you. So if I have the 2 to the power of, this is 30. This is my highest frequency. Also, I can put it down. Highest frequency is easy because these two are 0. Remember, I said this is 0, this is 1. If I put down this number, you can also understand it. 2 over 0 and 1. So this one is easy. This one, you can understand this is 1 mega. But here, if you want the low part means this maximum and this maximum. If you use the lowest frequency for the low part, it becomes 30. Make sense? For the highest, I put down 0 and 1. And for the lowest, 7 and 2 times 256. And I can calculate them. So now I'm gonna just pause this one right in here. I'll continue with the rest next week. Log into Avenue quickly, and I'm gonna just activate your quiz. Meanwhile, anyone who has a question for me, feel free to come see me. I believe I forgot to share my screen while I was doing all of those for you.